Hello, everybody, and welcome back to Calculus 3 online at FCC. In this video, I will start discussing the chapter for critical points and max-min problems. Now, it is a fairly involved topic, so I've decided to split it up in several parts. And in this particular video, we will discuss finding critical points and also classifying them. So before we get into the new material, I wanted to remind you what we've done in Calculus 1. Here, you see a graph of some polynomial function. And what we've done in Calculus 1, we said, let's go ahead and compute the derivative of f. Let's set it equal to 0 and then solve for x. And if we can do that, then we will be able to find the values of x where the derivative is 0. And that means we can find the points where the function will be changing behavior, right? So here on the graph, I'm going to mark those points where my function is changing its behavior either from increasing to decreasing or the opposite, okay? And this is not surprising because this is where we have horizontal tangent, right? Which is equivalent to saying the derivative at these points is equal to 0. Moreover, we can split the domain of this function into these subintervals where the function is increasing. So I'm marking it with purple. So these are the subintervals where the function is increasing, or equivalently, the derivative is positive. And then we can also do a similar type of thing for the function, or for the intervals where the function is decreasing. So over here, okay, where the derivative is negative, and that will tell us what type of points we have. So we would say that this first point, x1, this is where we have local maximum. And we also have another local maximum right here for x3. Okay, and then the other two points where the function is changing from decreasing to increasing. That's where we have local minimum, right? So this is a local min, and then also local min over here. Okay, so that's the first thing we've done in Calculus 1. Also, we could say, all right, what if we are not concerned about the entire domain and we just want to look at this function on a bounded subinterval? Okay, so let's say we want to look at this function on this interval right here. I'm going to go ahead and put a window around it. Okay, so something like this. And now, what else do we need to do? We still consider all of those points that we marked on the graph. But in addition, now we need to look at the value of the function at the endpoints, right? So we would look at our function and see what is it for the left point and for the right point. Okay, that bound the interval. And then from here, you can see that once we do this, now we have the absolute minimum over here. This is absolute minimum. And over here, that looks like this is absolute maximum, right? That's not always the case, of course. It's just for this particular situation. That's how it worked out. All right. So I want you to keep this picture in mind as you are learning this chapter's material, because now what we're going to do, we're going to extend this idea to functions of two variables. In Calculus 3, our functions are now have two variables. Okay, and now the graph of a function will be a surface, which is not so easy to visualize without technology, right? But the idea will be the same. So today, in this particular lecture, we're going to learn how to determine those critical points, which will be candidates for extreme points, right? So candidates for those points where we might have local max or local min, okay? And I'm gonna discuss 3 examples total. And then in the next video, we will extend that idea to the bounded portion of the domain, okay? So what is that going to look like for a function of 2 variables? All right, let's go ahead and take a look at the definition of critical points. So for a function of 2 variables, we say a critical point is a point where one of these is true. We either have that the partial derivatives, both of them, are simultaneously equal to 0, okay, or one of the partials does not exist, okay? So one of these things needs to happen for a point to be considered as a critical point. Okay, now most of the times, most of the problems that we will discuss, we will have the first condition satisfied, that our derivatives, our partials will be 0. And this is simply because the examples that we are using for this class are mainly polynomials and they are differentiable everywhere, so we're not going to have non-existence. But we need to keep in mind this can happen, especially if we're dealing with a rational function. Okay, let's go ahead and solve this problem. Here we're just determining what the critical points are. Okay, how do we do this? So in general, we need to solve the following system. The first derivative of f with respect to x needs to be 0, and the first derivative of f with respect to y also needs to be 0. Okay, so this needs to happen simultaneously. Okay, and what our points are going to look like, they're going to have coordinates, right? Let's say x null, y null. So keep that in mind. Once you find these values, you can label them with letters to represent points. You can also check if they produce the result that we want, meaning both the first derivative with respect to x and with respect to y need to be 0. Okay, so now we're going to compute these derivatives. So what do we get here? For f sub x, this is going to be 3x squared minus 3 is equal to 0. And then the derivative with respect to y, so partial here, what is that going to be? That's going to be 3y squared minus 12y is equal to 0. Okay, so I'm writing this as a system because I need to make sure that these conditions are satisfied at the same time. Okay, so from the first equation, we get that x is equal to 1. I'm sorry, x squared is equal to 1, right? So if I put the negative 3 on the right side and reduce by 3, that's what I get. And over here, we can reduce by 3 and factor y. We're going to get y times y minus 4 is equal to 0. Okay, so we are almost ready to write out our points. From the first expression, we get x is equal to plus or minus 1. Okay, and it's important to keep that in mind. If you have quantity squared is equal to some number, then that quantity x is plus or minus root. In this case, it's 1, right? And over here, we have either y is equal to 0 or y is equal to 4. So this is product of two numbers is equal to 0. That happens when either one of them is 0. Okay? So what do we conclude from here? Okay? From here, we say we have 4 critical points. Okay? So let's see what they are. I'm going to go ahead and label them. Let's say point A. If x is equal to 1, then y could be either 0 or 4. So let's say 1, 0. That's my first point. And then 1, 4. Let me fix that. Okay, is another point. All right. And then third point would be let's call it C, -1, 0, okay, and then point D is -1, 4. Okay, so these points right here, A, B, C, and D, these are what we call critical points. They are candidates for extrema. Okay, so they are candidates for the locations where we might have minima or maximum. All right, so that's your first example. All we're asked to do here is to compute or to determine critical points. All right, now let's go ahead and take a look at the following test. We're going to call it second derivative test. And this tells us how to determine what type of points we got. Okay, so what we're going to do, essentially, we're going to compute the following quantity. We're going to call it discriminant. It's a function of x and y that is going to take some values, right? And how do we compute it? So it's going to be second derivative with respect to x times second derivative with respect to y minus the mixed derivative squared. Okay, so this is the quantity that we'll need to compute if we would like to classify our critical points. And here you see some conditions that we need to check that will tell us, excuse me, what kind of point we got. All right, so let's take a look at the first condition. It says that if D is greater than 0 and the second partial with respect to x is less than 0, then we have a local maximum. Okay? Then if D is greater than 0 and the second derivative bigger than 0, then we have a local minimum value. Okay? If the discriminant is less than 0, this is what we call a saddle point. Okay, you do not need to check the value of the second derivative. And what is this? What is the saddle point? Okay, so we haven't discussed that yet. Okay, remember our graph is a surface, and you can kind of visualize a saddle, a little saddle that you would put on a horse, right? Well, if you can imagine that if we have something that looks like this, so this is kind of me representing a saddle, you know, a portion of it, and let's say there is a point over here. Okay, so what does the saddle point look like? It is a point where if you go in one direction, let's say you go along this curve right here, you're going up. But then if you go in along a different path, so let's say you go this way, then you're going down. Okay, and that's what a saddle point would look like. The way that surface is curved, what happens if you go in one direction, you're going to be going up on the surface, but if you go on a different path, you're going down. All right, so that doesn't happen for, let's say, local maximum. Let's say we have a upside down paraboloid that looks like this, right? And let's say you're standing right here at the local, well, that's not local, this is actually absolute, right? So here's your absolute maximum. Okay, so when you're at the absolute maximum point, no matter which direction you're gonna go, we're gonna be going down, right? We're gonna be decreasing. Okay, the value of the function is decreasing. All right, so that's the difference between absolute max and min and then saddle point. So that's what a saddle point looks like. And then if that quantity D is equal to 0, then the test is inconclusive, in which case we need to find a different method to determine what type of critical point this might be. All right, so let's go ahead and solve a problem, a couple of problems where we apply this formula here. Okay, so the first step is the same as in the example number 1. We need to find partial derivatives, set them equal to 0, solve for x and y. Okay, so that's the first step. Let's go ahead and go through this solution. Okay, the first derivative with respect to x, that's going to be 6xy minus 12x. I'm going to set it equal to 0. And then partial with respect to y is going to be 3y squared plus 3x squared minus 12y is equal to 0. Okay, so that's the system I need to solve, okay, with respect to x, with respect to y. All right, how do we go about it? Oop. Okay, let's return. Okay, what do we do? Let's see. For the first one, I'm going to reduce by 6 and then also factor out x. So that's going to give me the following expression. X times y minus 2 is equal to 0. All right. What happens in the second equation? Here, the only thing that I can do is reduce by 3. So this is going to be y squared plus x squared minus 4y is equal to 0. Okay, so now we take a look at it and say, well, what do we do? How do we solve this system? Now we have a nonlinear system, right? You see, the second equation has squares in its powers, okay? And the first equation has x times y. This is a nonlinear system, okay? If you take in a linear algebra class and you attempted to solve this system with matrices, you can't do that, okay? This is not one of the systems that we can do with linear algebra. And that's the tricky part of these problems, because there's no clear one-way method to find the critical points dependent on a function. We'll have to just apply our critical thinking skills to solve these systems. But typically, one of the equations will kind of give you a way to find it. So I'm looking at the first equation. In the first equation, I have a product of two things that's equal to 0. That means from here, we have either x is equal to 0 or y is equal to 2. Okay? Remember, these two equations need to be true simultaneously. So if neither one of those is true, it doesn't matter what we find for the solutions in the second equation, okay? X is either 0 or y is equal to 2. So now we're going to consider two cases, okay? So case 1 is when x is equal to 0, okay? So we're going to take care of this case right here. If x is equal to 0, then we can plug that into the second equation. And once we do that, we're going to get y squared plus 0 squared minus 4y is equal to 0. And that is easy to solve because now we have one variable. And from here, we can see that y is equal to 0 or y is equal to 4. Okay, so let's highlight this. This is going to go with this condition. If x is equal to 0, then y is either 0 or 4. That's going to give us 2 points. Okay? Now, let's see. What about case number 2? So for case 2, we say, okay, if x is not equal to 0, then y has to be equal to 2. So we write y is equal to 2. And what do we do now? We plug that 2 into the second equation. So that gives us 2 squared plus x squared minus 4 times 2 is equal to 0. And once you do all the arithmetics, we get that x squared is equal to 4. So from here, x is either positive 2 or negative 2. Okay, and this solution goes with y is equal to 2. Okay, so now we have the following candidates. Let's go ahead and label them. So what are our candidates? All right, so A let's say x is 0, y is 0. That's going to be point A. Point B, x is 0, y is 4. Okay? And then let's call the next point C. We've exhausted this scenario. So now x can be 2 and y is also 2. Or point D, where x is -2 and y is equal to +2. All right, so this is what we have for the points that are critical points. That's the first part. Now it says classify. Okay, what do we do now? Second part, we're going to compute that quantity. Okay, all right, so now we do what? We're going to compute the second derivative with respect to x. The second derivative with respect to x, let me write it over here. What is that going to look like? That's going to be 6y minus 12. Okay, and then the second derivative with respect to y, let me write it over here. That's 6y minus 12. Okay, it's the same thing. So now we do what? Okay, 6y minus 12 times 6y minus 12 minus, let's see, the partial or the mixed one, right? F sub x, y. What do we get there? So I'm going to go back over here. And here, what do we get? If we differentiate this with respect to y, we're going to get 6x. Okay? So now I know what this expression is going to look like. 6x minus 12 squared. We don't need to multiply this through, by the way, because we just need to determine the sign of this quantity here. So that's our discriminant. Okay, now let's go ahead and evaluate it. So the next step is evaluating. Okay, evaluate D at our points. Okay, let's see. So D evaluated at A, and I'm going to go ahead and let you confirm this. That's going to be 144, which is greater than 0. So I know that I'm going to fall into either this category or this one, either 1 or 2. So then I determine what my second partial looks like at A, and that turns out to be -12. That's less than 0. Okay, so what does that mean? If it's less than 0, that means point A is local maximum. So I'm going to go ahead and mark it over here. This is where we have local maximum. All right, let's do the same thing for the rest of the points. So D evaluated at point B. It is also 144. That's greater than 0. Okay. The second derivative with respect to B is going to be 12. That's positive. I'm looking at my second derivative test. It is the second condition. Discriminant is is greater than 0. Second derivative is also greater than 0. This is a local minimum. Okay, so this point right here is local minimum. All right, then D evaluated at C. I'm gonna let you figure this one out. This is -144. That's less than 0. And similarly, you'll see that D evaluated at the point D is also -144. That's also less than 0. These are saddle points. Saddle points. Okay. All right. So for this problem, not only did we find the critical points, we also classified them. Okay. So classification usually is easy. It is computing the critical points, that can be a little bit tricky because functions can look all sorts of different types, okay? All right, so that's our example number 2. Now that you've seen the process, let's go ahead and solve example 3, and we'll go through the steps a little bit quicker, so you already know what to do, right? But let's just work through this solution. Okay, I have a function of 2 variables, and it is a polynomial function, so I know my derivatives will exist. That means I need to compute the partials, set them equal to 0, and solve for x and y. All right. Okay, let's see what the partial with respect to x is. That's going to be 4x cubed minus 4y. That's equal to 0. And then similarly, the partial with respect to y is going to be 4y cubed minus 4x. We're going to set that equal to 0. Okay. You can see how these equations are very similar, right? Let's go ahead and reduce it by 4. We're going to get x cubed minus y is equal to 0. And then here, we're going to get y cubed minus x is equal to 0. Okay. So now what we have here are 2 equations that look very, very simple, but it might be a little bit counterintuitive on how to solve these. Okay. By inspection, you can see what numbers will work out. Okay. You can see that, oh, if x and y are both 0, that's definitely going to work. But how do we actually solve it algebraically? So what I recommend you do, if it's possible, write one of the variables in terms of the other and then substitute to the second equation. So what I'm going to do, from the second equation, I'm going to say my fundamental relationship will be that x is equal to y cubed. Okay. And then I'm going to plug it in over here into the first equation. All right. And you'll see why I'm going to do that. So x cubed minus y is equal to 0. If I substitute y cubed in here, now this is what my equation is going to look like. So this becomes y to the 9th minus y is equal to 0. Okay. And if I factor y, I'm going to get y to the 8th minus 1 is equal to 0. So it's either y is equal to 0 or y to the 8th is equal to 1, in which case we have y is equal to plus or minus 1. Okay, so this is how we solve our equation, keeping in mind that right here is our fundamental relationship between x and y. Okay, so let's see. Let me go ahead and emphasize the following, that we have the following: x is equal to y cubed, and our y is either 0 or 1 or negative 1. So from here, we're going to get the following points. These are our points. A, okay, A is going to be, if y is 0, then so is x. Okay. Point B, well, let's see. If y is 1, x is 1 cubed, then x is also 1. Okay. And then the last one, if y is negative 1, then so is x. Okay. Now let me go ahead and make this note that, let's say you decided to put this point right here. Okay. 1, negative 1, or negative 1, 1. That's not going to work. These are not critical points. Okay. Are not critical points. And why is that? Because they will not satisfy this relation right here. X is equal to y cubed. Okay, so we might be tempted to include them also as points. It's not always going to be the case. Okay, if x is equal to y, yes, then we would include those combinations. But that's not the case. X is equal to y cubed. Okay, so we cannot have that alternating sign in there. So these are the 3 points that we need to consider. Okay, so now what is the second step here? We need to classify them, right? So what is our discriminant? Okay, I'm gonna let you confirm that once you follow this formula, f second derivative with respect to x times second derivative with respect to y minus our mixed derivative squared. Okay, once you follow through all the steps, we're going to get 144 x squared, y squared, minus 16. Okay, it is a function of x and y, and it will tell us something about these critical points. So now let's go ahead and evaluate it. Okay, that's the last step that we're going to do. So discriminant for 0, 0, easy to evaluate. That's going to be negative 16. This quantity is less than 0. So we say this is our saddle point. We don't have to have a saddle point. Sometimes we won't. In this case, we get 1. Okay. Then if I evaluate at my point B, so this is 1, 1 for x and y. Okay. Once I do that, it's going to be a positive number, right? We don't even need to compute it necessarily. We just need to determine the sign. So this is positive. Okay. And then we evaluate the second derivative with respect to x at that point. That is, what is that going to be? It's going to be 12, and then this is positive. So if the discriminant is positive and the second derivative, what do we get? We get a local minimum. Okay, last portion. Okay, at C, what are C coordinates? Negative 1, negative 1. We again get a positive value for the discriminant. And once we evaluate the second derivative, carefully plug this in, we're also going to get 12. So that's greater than 0. That is also local minimum. Okay, so that's how you would proceed with a problem of this type. All right, so let's go ahead and quickly review what we've done. Okay, the first thing is that we learned how to compute these points, right? How to determine them. And just a little bit of a warning, it can be a little bit tricky at first because of the way the systems work out. They're not linear. They're not always the same. We might need to use different tricks depending on the problem. So we learned how to compute critical points. Then we've learned about second derivative test. Okay, so that quantity D, you don't need to memorize any of this. Have your notes in front of you, right? And for the exam, you could have a formula sheet with all of that written down. So carefully follow the rules to determine which type of point we have. Okay, so we evaluate our discriminant for these points, decide on whether we have local mix, local max, local min, or saddle point. Okay, and over here, this is the first system where we discuss the fundamental relationship between the two variables, right? You could have also picked that y is equal to x cubed, and you would have come up with exactly the same solution. Okay, so the points would be the same. Find the points evaluated. Okay, we're gonna go ahead and stop right here. In the next video, I will be discussing maxima and minima for functions when their domain is bounded. Thank you for watching, and I'll talk to you next time.